Hello friends, I am here with a question from JEST 2020. This question is about thermal conductivity. It says a rod consists of two equal sections of length L each with coefficient of thermal conductivity kappa 1 and kappa 2 respectively. One end of the rod is kept at a fixed temperature T1 and the other end at temperature T2, where T1 is greater than T2. If kappa 2 equals to 2 times kappa 1, then the temperature at the interface is. So we basically need to find the temperature right here. Let it be Tx. Okay, this is the interface. We need to find the temperature here. And it also says that the temperature at 1 is greater than the 2. So heat will flow this way. That we can ascertain. Now, the next thing is coefficient of thermal conductivity. Now, what does that mean? There's a thing called heat flux, okay, which we usually denote by Q. Now, the heat flux is the amount of heat that flows per unit area per unit time along this, okay. So that is the heat flux. Now, this heat flux is proportional to the difference in temperature divided by the length, and the coefficient here is the coefficient of thermal conductivity kappa, T2 minus T1 divided by L. Okay, so that is the coefficient of thermal conductivity. However, in our case, we have got two conductivities for two parts of the rod, which means what we do is we'll take the nice thing about flux is that it is the rate of energy, right? So if 5 joules of energy is flowing per second right here, then even here only 5 joules of energy can come out, no lesser, no greater. Okay, and we'll be using that property. It follows from the conservation of energy, right? Energy can neither be created nor destroyed. So if 5 joules of energy comes here, okay, per unit area, the area is same, and per unit time, if 5 joules come here every second, 5 joules have to leave every second. So what we have is the flux right here, let's call it the flux here, let's call it Qx, and here let's call the flux Q2. Then what we do have is, firstly, how will we find Qx? Well, the flux Qx will be equals to Tx minus T1, because that will be the difference in temperature, divided by L, right? Divided by L, and in front of it we'll have the coefficient of thermal conductivity kappa 1. Next, Q2, that is the flux here, will be equals to T2 minus Tx divided by L, and then here we'll have kappa 2. Now, as I said earlier, Qx must be equals to Q2. So what does that mean? It means that the right hand side of these two are also equal. So let's solve that equation. Kappa 1 equals to, kappa 1 times Tx minus T1 divided by L equals to kappa 2 T2 minus Tx divided by L. So we can cut off the L's, and we have got kappa 1 Tx minus kappa 1 T1 equals to kappa 2 T2 minus kappa 2 Tx. And write this as Tx kappa 1 plus kappa 2, which is equals to kappa 2 T2 plus kappa 1 T1. Now I'll use the property that we are given in the question. Kappa 2 equals to 2 times kappa 1. So what we'll have then is Tx. Now kappa 2 is 2 times kappa 1 plus kappa 1, which is equals to 2 times kappa 1 T2 plus kappa 1 T1. This gives me 3 times kappa 1 equals to kappa 1 2T2 plus T1. This implies the required temperature is 2T2 plus T1 divided by 3, and that is our answer. Okay, so 2 times T2 plus T1, 2 times T2 plus T1 divided by 3, and this is our answer. If you have any doubts, suggestions or comments for this video, please write it down in the comments below.